one of those important reminders being that I have to set up the YouTube live stream. I want to remind you all that we do have a code of conduct that we expect everyone here to obey and follow. And if you haven't read it, it's linked on our pages. And you can find the information on the main website for the workshop. And I'd also like to remind you all that we are requiring masks to be worn when you're in the room to help reduce, and we have some masks in the back if you need any. And also, I would like to point out that we can use this door. We will probably prop this door open at some point, so you can go in and out this way, you can go in and out that way. And then later on, the reception will be in the courtyard, which is in the main entrance, but I'm sure we can all ferry over together if we can't get there individually. Thank you.
All right, thanks, Rudy. I'd like to welcome everyone as well. This workshop was something we proposed a few years ago. Comes out of some work that myself and Carlos and Herman Lee and Pat and others have been doing, trying to understand this. And I'm going to stop talking, except to remind people that contributed talks are 15 minutes long. Lightning talks are 5. There's time during breaks for questions if you would like to stick to our schedule. Invited talks are 30 minutes. We'd like to have a couple minutes at the end for questions. I will be running the timer, and I am a strict timekeeper. So without anything else, I'd like to introduce Pat Swain, who's the director of the Chandra X-ray Center, for a few opening remarks. So Pat, if you will.
Thanks, Dan.
Yep.
Okay, so how do I find this slide? So hi, everyone. Welcome. Thanks for coming. There's the title slide, but actually, not yet. There we go. And in presentation. There we go. Right. So as Dan said, actually, it's not showing. I'll just keep talking. This workshop on the topic of supernova remnants and the progenitors comes out of a long research avenue of inquiry. There we go. And it's really a pleasure to see the group that's here as well as the group that's joining us online. This is a series of annual workshops that are held by the CXC on a variety of different topics. Some of you may be old enough to have been at previous supernova remnant ones. There have been some in the past. For the meeting, I just just like to mention already, we have the science organizing committee and the local organizing committee listed over here. We've already heard from Laura, who's the co-chair of the SOC. Rudy has led the way in arranging a large amount of the details of this meeting, as well as ones in previous years. And Dan, whose expression is either saying, I'm a little worried about this meeting, or you're going to fit what model to those data, has done a heroic effort in doing the arrangement of this while he's simultaneously been working nights and days on an instrument anomaly for the spacecraft that he'll be happy to tell you about later on. So let me just very quickly set the stage for where we might go in the context of Chandra as supernova remnant tool. And I want to set that stage by noting that at a workshop somewhere before 1999, I was sitting with a colleague who shall remain nameless, who was talking to me about the fact that it would have been nice if Chandra had been optimized for supernova remnant research. And in fact, the phrase used was actually that it was pessimized. It was actually done completely wrong for this because the field of view is small. The resolution is good, but the collecting area isn't that large. So the individual pixels won't be that filled with photons. And so really, it wasn't what we really needed. It'll be okay, but it won't be what we really needed. And so I just have a gallery here of things that illustrate exactly what it was about Chandra that led to the spectacular results that have contributed to a field that, of course, is being, complemented with other instruments across the wavelength band. But, with CAS-A, immediately, the first light image, the resolution shows us that the neutron star that had never been seen before was there. We identified the torus jet structures in pulsar wind nebulae and how complicated they can get. And when they're out in the interstellar medium, how they somehow have particles streaming away from them and jumping onto the fields in the ISM. The high resolution camera allowed fast timing to detect pulsars early in the mission. Of course, another image of CAS-A illustrates that you can go with small regions and identify knots with completely different elemental structures. If you're bold, you can even put a rating in front of a supernova remnant and get spectra. And that's just the start. The other point, I mean, that all comes because of the structure of the telescope. But then there's other elements of it that have to do with the fact that pre-1999, I suspect that my colleague thought that Chandra was going to be a 3-year mission. That's what its requirement was, with a goal of 5. But when you get out to 10, 20 years, then suddenly you can do things with that high resolution, like see these supernova remnants expanding, see pulsars in supernova remnants moving. I think we'll probably hear more about that later on. Follow the evolution of supernova 1987A through its lifetime. And these combinations of exquisite capabilities plus longevity have just really allowed Chandra to contribute to this field that we all are so interested in. So the last thing I'll say is, we anticipate continuing to do that. We're certainly still operating. We're still doing observations of all sorts, including those in our own field. And so this usually says what comes next, but what supernova remnant comes next is the obvious question for this audience. And so I'll leave us there. Let us walk into the talks. Hope you enjoy the workshop. There's going to be a lot of very interesting things that we're going to hear in the next 2 to 3 days. Thanks.
Hey, Pat, thank you. And I'm going to speak loudly so that I don't have to keep flipping the thing. We have a number of virtual talks this morning. And I'd like to start by welcoming Toshiki Sato from Rikyo University. Toshiki will be telling us about, X-ray observations of rare metals in supernova remnants. This is a contributed talk, and so 12 minutes plus a few minutes for questions. So Toshiki, if you'd like, you can get started when you want. Thank you.
Can you hear me?
Yeah.
Okay. Thank you for providing us this great opportunity. This is Toshiki Sato from Rikyo University. Today I'm going to talk about X-ray observations of rare metals in supernova remnants. This result is based on our recent paper published in 2020 and 2021. So if you'd like to know more detail, please read this paper or please ask me on Slack. Anyway, let's start my talk. I'm interested in connecting pre-supernova or supernova theory to remnant observation. And actually, there is a gap between the theory and observation. In particular, supernova theory and remnant observation, there is a more larger gap between them. So we are trying to connect them using the SNL observations. And now we were collaborating with the theoretical researcher with supernova theory and the nuclear synthesis. And then we noticed some rare elements of the remnant will be very useful to connect the theory and observations. So today I'd like to introduce some our recent results relating to this topic. Before talking about the detail, I'd like to briefly introduce nuclear synthesis in quark-gluon supernova explosion. Here, I'm focused on the innermost silicon bonding layer. This is because this layer, in this layer, only a few physical parameters can determine the elemental composition. This is a 1D nuclear synthesis model, and the silicon bonding layer is here. Then our main product is ion group elements. Then those elements can be determined by temperature and density and evolution of these parameters, and also electron fluxation. So to measure these elements, the elements around iron would be very useful information to understand explosion mechanism and also the progenitor story. So today's topics is here. First, I'd like to introduce manganese over coal mass ratio. We think this is produced at incomplete silicon bonding layer and here. This is related to the progenitor metallicity. And the second one is titanium and chromium observation at innermost layer, complete silicon bonding layer. These elements are related to the explosional dynamics. In other words, entropy during the explosion. And also in the final slide, I believe we introduce future X-ray calorimeter emissions. Actually, I'm a member of the CRISM emission. Then we believe the X-ray calorimeter will be a game changer for such a rare metal measurement in supernova remnants. So let's move to our detailed topics. First one is related to the progenitor science. Cas A is known to be a 2B type 2B supernova. This is light echo spectrum from around the Cassiopeia supernova. Then we can see this block curve shows Cas A, and this gray one is 93J. And these are very similar to each other. Based on this result, the Cas A's progenitor thought to have almost stripped hydrogen envelope, like this schematic view. And in the case of Cas A, the progenitor total ejector mass is around 3 solar masses or something. This means our progenitor star is not so massive. From these results, probably the progenitor star Cas A have a binary, is a binary, and we need to know the wind muscles history to understand their such a progenitor system. And the initial metricity is one of the most important parameters to understand its mass loss history. However, it was difficult to discuss initial metricity in the previous studies. So here we are focusing on the manganese and chromium mass ratio for discussing the initial metricity for this progenitor. Actually, this is usually used for the type 1A cases. However, it has not been used for our type quark-gluon case. And our conclusion is, in the case of the quark-gluon supernova remnant, manganese over chromium mass ratio can be used for the progenitor, discussing progenitor metricity. And here, high initial metricity means high manganese over chromium mass ratio. And if we could measure the manganese and chromium mass ratios, we could discuss initial metricity. However, it is a little bit difficult, complex, rather than the type 1 cases. This is because interior structure of massive stars are more complex rather than the type 1 cases. For example, these are progenitor models, are electron fraction profile in the interior. For example, different color means or different metricities. And here we can see general trend from upper side to the lower side. This is a metricity effect. However, there is a step-like structure like these. These are electron capture effect during the stellar evolution. And these positions are different from model to model. So there is a large uncertainties on the stellar evolution as progenitor models. However, our conclusion is Cas-A has a low manganese over chromium mass ratio. This is a very robust. And comparing with the many progenitor models, probably this remnant progenitor should be the subsolar metricity. So if the progenitor with subsolar metricity this is a very interesting because again, Cas-A is known to be a type 2b. And a subsolar metricity progenitor suggests in the case of Cas-A, the binary progenitor. And however, there is no obvious companion star in this remnant. This is very interesting. So now we are discussing some scenarios to remove the hydrogen envelope. First is a compact companion scenario. For example, if the companion was a black hole or something, maybe we can explain non-surviving companion in this remnant. However, it was very difficult to observe isolated black hole on the center, so it is difficult to conclude. And also, we are proposing a new scenario. This is the first supernova in binary system strip the hydrogen envelope for the second supernova. This is proposed by Ryosuke Hirai in the Monash University. This is also interesting scenario. However, there is no conclusion, but Cas-A will be a very unique target to investigate such mass loss histories for the strip envelope supernova remnant. And also manganese over coal mass ratio can be measured in the future. So maybe we can develop these topics in the future. And the next topic is there are elements in the iron-rich plumes in Cas-A. And here, this is an X-ray image of the Cas-A. And we can see iron-rich plumes in Cas-A. This is a very interesting feature in this remnant because iron should be produced at innermost area of exploding star. So this ejecta should be produced at inner side, and then some asymmetric effect should push this structure during the explosion. For example, this is a three-dimensional simulation of the supernova, and we can see iron-rich plumes like this, and these are thought to be comes from the high entropy bubbles from neutron during convection. So our questions, we can discuss such a structure using X-ray observations. Then we are searching for rare metals like chromium and titanium in this structure. This is because these elements should have sensitivity to the entropy during the explosion. And then this is our new results. We found the titanium and chromium in the X-ray spectrum from the iron-rich structures. Then these mass ratios indicating this iron-rich ejecta could be the high entropy ejecta plumes from the neutrino convection. I cannot explain the detail, but this will be related to the explosion mechanism for supernovae, and we think these are very important results to understand the collapse supernova explosion. And as a future works, accelerometer will be very helpful to understand the rare elements production in the remnant. For example, this is a red curve shows a Chandra spectrum, and the blue curve shows a Prism spectrum. We can see many tiny structures like here. So these will be very helpful to understand nuclear synthesis and our explosional dynamics in the for collapse supernova explosion. So I hope those missions will be succeed in the next decades. And that's all. Thank you for listening.
But I think the thing to do is if we have online questions, we should address those first. And then I will start calling out people in the audience who might have questions for Toshiki. So I see we have two people who have questions on the virtual panel. And feel free to, I don't know who they are, so. So
We have Martin Lammy.
yeah, so Martin, why don't you go first?
Okay, my question is, a possible scenario for the binary companion was that it was an M dwarf that merged with the progenitor before the explosion, and that's where the hydrogen comes from. So you've added, let's say, half a solar mass of hydrogen to what was originally going to be a type 1 supernova. Is that plausible? Is it type 2b because it's had hydrogen added to it by the binary companion?
You mean the compact this scenario?
The binary companion that was stripping the wind has merged with the progenitor. And that's why it's a type 2b and not a type 1 BC or type 1, yeah, because the hydrogen that you're seeing has come from the what was originally the companion.
I think it is interesting, but
you probably can't really say. It's just an idea for now, but I just thought I'd mention it.
I couldn't answer for now, but yeah, such a scenario really really interesting. Thank you.
Okay, very nice talk, by the way. Thank you.
Thank you very much.
And next we'll go to Ray.
Yeah, so let me reiterate, that was a very nice talk. I enjoyed it very much. Can we go to slide 8? I think it was.
Which one?
Slide 8.
Slide 8. This one? Yeah.
Yes. So I think it looked like you were using 1D models for your nucleosynthesis predictions.
Yes.
I'd caution a little bit about that, because one of the things we find with multi-D models, especially with the way the entropy affects the ejecta, is in a 1D model, you have a very strong dichotomy between the entropy gain of the innermost regions and the outermost regions, which is somewhat mitigated in multi-D, because instead of heating the bottom a lot, you heat a train of material as it comes through. So that would shift the lines pretty significantly, I think, given what we've seen and what Fryer and those guys have seen too. So just a word of caution for your analysis.
Yes, I agree with you. Actually, yeah, this is a 1D model, and for example, 3D models have a different thermal evolution for such structures, and probably we need to compare with such a 3D multi-dimensional simulations. However, this observation, yeah, but we don't have such a statistical data. So please, if you have some multi-dimensional models, please compare with this result. And actually, this is a not strong conclusion. So I'd like to discuss with theoretical researchers to understand the more realistic solution for explaining these mass ratios. So yeah, I agree. I totally agree with you.
Okay, thank you.
And I see Noam, of course, reminds us to consider the jets, which it's certainly casse. The jets are, whether they're a byproduct of the explosion or not is something that lots of people have lots of opinions on. So at this point, do we have any questions in the audience? I see Carlos is raising his hand. No? Okay. Oh, do we have any other questions online?
Salvatore Orlando.
Okay. Yeah. So I think the nice thing about the Q&A is that if people want to continue the chat online, they can certainly do that. Also, if they want to raise their concerns and actually voice them, that's something they can do too. Okay, I don't see any other questions here in the audience, and I don't see any other questions online. So let's thank Toshiki.
Thank you. Thank you very much.
Thank you, Toshiki. And let's move on to our next talk. This is a lightning talk by Dmitry Shishkin, supplying angular momentum to the jittering jet explosion mechanism using convection in the inner layers of the star. So this is timely because jets were just mentioned. So thank you, Dmitry. This is 5 minutes, so you can talk for up to 5 minutes, or we can leave a minute or two for questions.
Right, thank you. Can you hear me just fine? Yeah. Thank you for the opportunity to present my research. I'm Dmitry Shishkin from the Technion in Israel, and I'll be talking about the jittering jets explosion mechanism of core collapse supernovae. Right. So what is the jittering jets explosion mechanism? As a massive star evolves towards the end of its life, it develops a massive core. Within several hours of it beginning silicon burning, it forms an iron core, which then collapses, forming a compact object, exploding the star. That's a core collapse supernova. The jittering jets explosion mechanism is a mechanism of explosion for the core collapse supernovae. Alongside the delayed neutrino-driven explosion mechanism, the jittering jet explosion mechanism sources the energy for the explosion from the gravitational potential of the collapsing star. According to the jittering jets explosion mechanism, it is perturbations in the inner layers of the star that cause stochastic angular momentum fluctuations of the accreting layers that, as they reach the proton-neutron star, form accretion disks that then launch jets. Because the angular momentum is stochastic, you'll have different disks forming different jets in different directions. And overall, these jets are what fuels or what sources the energy for the explosion and explodes the star. So we have the layers collapsing onto the proton-neutron star, forming accretion disks and launching jets, which explode the star. So the very basic question would be, is there enough angular momentum to actually cause the formation or to seed the formation of these accretion disks? And the answer to that would be yes. In this work, what we did was look at the convective velocity of core collapse progenitors at the moments leading up to collapse. So in this case, we have a 15 solar mass progenitor star, and we're looking at 3 panels over here. It's 3 times. This one is 3 seconds before the collapse, and this one is a fraction of a second after the collapse has already begun. You have an inflow velocity of over 1,000 kilometers per second. And what I wanted to focus on is the red line here. The x-axis is the mass coordinate. The red line would be the convective velocity scaled on the left. And you see that as the star collapses, you have a vigorous convective region forming at the edge of the silicon, at the edge of the iron core, with convective velocities upwards of 400 kilometers per second. Now, if you multiply that by the radius, you get enough specific angular momentum to see the required perturbations to form these accretion disks. So if we say that we do have enough specific angular momentum to form the accretion disks and launch the jets and explode the star, the next question would be, what would be the remnants of these? And if we look at the innermost convective zone that has enough specific angular momentum to explode the star, we can then say that that would be the mass of the remnant. In this graph, in the x-axis, we have the masses of the progenitors, and the y-axis would be the mass of the remnant. The colored blobs here are the convective regions that have enough specific angular momentum. So if in this convective zone as accreted forms these accretion disks, everything below the mass coordinate of this convective zone will be accreted onto the neutron star, and everything above that will be exploded away in the supernova. So that will be the mass of the remnant. Now we see here that for the lower edge, we have a mass of roughly 1.4 solar masses. In the higher masses, we have a mass of roughly 1.8. Both of these are completely consistent with neutron stars, so that's reassuring. Now, what would be the next step? The next step would be, after we've shown validity, we intend to show that at least in some cases, the jittering jets explosion mechanism is not only possible, but also preferred over the delayed neutrino mechanism. And binding energy is a clue to how we might be able to hint at that. Right, that's all I wanted to show. Do check out on Wednesday, there's a talk by Noam Suker and a talk by Mohammed Akashi regarding jets and supernovae. Thank you for the opportunity again. Thank you for listening, and I encourage questions on Slack.
Thank you, Dimitri. That was well rehearsed. That was 5 minutes on the dot. I see that Rob has a question. So Rob, we have time for one question. So Rob, go ahead.
I have to unmute him, sorry.
Okay.
Oh. That was the wrong person.
Search for season.
There you go.
Do you have a question, Rob?
Yes, I was wondering, the case of Cassie really shows the jets, east-west, the south-west and northeast jets. Does your model match the velocities that you see in the Cassie case?
In this case, well, if you do look at supernova remnants, you have some evidence for jets. That's also one of the images I'm showing here. We'd have to model it in some more complicated way. Everything I've showed here is based on 1D simulations. So we've shown that the jittering jets explosion mechanism for the Kokolov supernova is possible, but from that to actually compare against observations is a bit much from these 1D simulations.
Okay, thanks.
Okay. All right, and as Dimitri had said, he encourages questions on Slack or other chat means. So thank you, Dimitri, and thank you, Rob, for that question. Moving on, we have a series of lightning talks this morning. Our next one is by Josephine Larson, who will be telling us about a 3D view of clumps and rings of ejecta in the supernova remnant 0540 minus 69.3. This is a 5-minute lightning talk. So Josephine, welcome.
Thank you very much. So I will present the 3D reconstruction of the ejecta in this remnant called 0540 minus 69.3. And I will take questions on Slack afterwards just to have a little bit more speaking time. And you can find more details about these results in this paper. So let me briefly introduce this work. So first of all, the reason we're interested in the 3D distribution of ejecta is that it probes the conditions at the time of the explosion. So it can tell us about the explosion itself and the progenitor. And observationally, we determine this from spatially resolved spectroscopy, where we simply use the fact that the distance from the center of explosion is given by the velocity and time since explosion, assuming we have a free expansion of ejecta. So this particular remnant, 0540, is about 1,000 years old. It's oxygen rich and located in the LMC. it has a rapidly spinning pulsar and a pulsar wind nebula. And on larger scales, there's also a shell of radio and X-ray emission. So we observed this remnant with Muse and X-Shooter at the VLT in 2019. And for this short talk, I will just focus on the Muse data. So this is an integral field unit with a field of view that perfectly matches this remnant. So I will jump straight to the main results. So if we start in the innermost region where the brightest emission is seen, we see small clumpy rings of ejecta. So these plots are showing isosurfaces of the brightest emission in some of the strongest lines. And the animation is just showing the sulfur and argon lines together. So this is low velocity ejecta inside 800 kilometers per second. And you see that the morphology in all lines is similar. So these elements are all mixed. There are even more interesting things if we move on to larger scales. So this is O3, first of all. So the results on the previous slide was just from this innermost region, but it's clear that we also see faint extended emission on larger scales. And this kind of halo had been noticed before, but with Muse, we could map this in 3D for the first time. And it turned out it forms a kind of large ring that surrounds the smaller rings. So that's what you see to the right. And this gray contour corresponds to just 3% of the peak emission, so it's very faint. And I will just remove the inner part here so you can see this ring-like structure more clearly, which has a radius of about 1,600 kilometers per second. And here I'm just adding in green the brighter contours from the inner region from the previous slides. There is one more very interesting thing on the large scales, which is a big blob of hydrogen. So there is a large area with H alpha and H beta emission southeast of the remnant. You can see it in the images here. It's blue shifted, so in 3D, it sits in front of this O3 emitting ring with respect to the observer. And assuming this is freely expanding ejecta, the full 3D velocities span about 1,500 to 3,500 kilometers per second. So what we conclude from all this, so it's clear that we have an asymmetric distribution of ejecta in the form of rings and clumps. And we provide various quantitative measures of this in the paper, and I'm just showing a couple of examples here. And the question is then how these structures are produced, and I'm hoping modelers will tell me. But I should, of course, point out that this is not the first time that we see rings of ejecta. There are other examples, like notably Cas-A. In the case of O540, it seems possible that the small rings might be nickel bubbles that are intersected by the shock in the pulsar wind nebula. The origin of the other structures is a bit more unclear. Perhaps this O3 emitting ring of ejecta reflects rotation of the progenitor. And as for this hydrogen blob, we cannot really rule out that this might be connected to a binary companion or CSM. So this needs to be more investigated in more detail. And I also just wanted to point out that, of course, the fact that we see these hydrogen lines in the inner ejecta confirms that this was a type 2 explosion. And in this work, we also derived an improved age estimate of 1,150 years. And just as a final point, I wanted to mention that we're working on other aspects of the remnant from these observations. So there are more results to come. And that's all. Thank you very much for listening.
Okay, thank you, Josephine. That's fantastic. The number of 3D remnants that we're getting now with Muse and other instruments is quite remarkable. For these lightning talks, I encourage people to submit questions on the Slack channel so that we can allow the speakers to present the most results that they can. And at this time, I'd like to welcome we're going to stay in Stockholm and our tour around the world. And our next talk is going to be by Bart Van Ball. It's a lightning talk, on nebula phase spectra in 3D non-local thermal dynamic equilibrium.
All right, thank you. If you can hear me? All right, great. So yeah, I will in the next 5 minutes briefly review the next or what I've done in the last few months on making 3D synthetic spectra of a 3D explosion model together with my collaborators. So to start off, before I explain why 3D is complicated, I'll start in 1D. So if you take a massive star, it will form in 1D an onion-like structure throughout its lifetime before it explodes, and then it ejects these as an onion-like structure, as you see here. And in 1D, this means it's relatively simple to make complicated models because you end up with maybe 100 zones total. And in this sort of model, the only thing that matters is how far away from the core of the explosion am I. It doesn't matter from what your polar or equatorial angles are. It doesn't matter from what angle I observe this. It's always going to look roughly the same. So in 1D, when we make these kind of models after a few months after explosion, we can stick a model into, for example, the code Sumo, which was developed by my supervisor. And the code will tell us, look, this is the sort of spectrum I'm predicting. And there are other codes that do this, but one of the main progresses we've made in the last few years is that we now have 3D explosion models, which look like this instead. And I think a lot of people can understand that if you try to turn this into ring-like 1D structures, it's not going to work at all. So we can throw most of the easy part out, and instead we're going to have to do this in 3D, which is much more complicated because now I also have to capture the equatorial angles, the polar angles, which results in way more zones to calculate. Like I said, a 1D detailed model has maybe 100. The models I'm working with have more of order 100,000 to 1 million. So you're ending up with so much more data that memory usage can become an issue. Your runtimes will become an issue. Like instead of 10 seconds, you're talking about timescale suddenly of days. 100 megabytes turns into a terabyte. So computationally, you really have to take great care in building such a structure. And to make it more complicated, if I take this remnant as pictured here, if I rotate this 90 degrees, it's going to look completely different. So I also have to take into account what does it look like from my viewing angle. So what the code I've built does is I tell it, well, okay, you're split into all these many cells. Each cell has a chemical composition, mass, energy deposition based on radioactive decay and a volume. And with these parameters, I can calculate its NLTE structure for every element. So the temperature in the cell, and then what is the excitation ionization structure of all the elements present there. And once I've fully solved that, I can ask every cell again, for all your excitation structures, give me an estimate of how much emission at which wavelength you're going to create. And then I can then take all of that and say, what happens if from this angle you are observed? What are all your Doppler shifts together? And then you can end up with something like this. My code currently doesn't do radiative transfer, so the line strengths are not exactly correct yet, but the line profile should be very correct. And one of the very interesting things, of course, is what happens if I take the same explosion model and I just look at one specific line profile from different viewing angles. So the line profile I'm going to zoom in on is the magnesium-1 feature here at 4571. And I've taken, all angles are taken at a 45-degree polar angle and then just around the equator. And then you get this sort of line profile evolution where you can see that based on your viewing angle, you can create roughly flat tops, you can create double peaks, Gaussian-like structures, very asymmetric things, which indicates that we can create a lot of different kinds of line profiles, which we observe in many types of supernova, but they might intrinsically be dependent on our viewing angle and not necessarily linked to one kind of supernova. But there's more work to be done there. And that was everything I wanted to talk. If people have questions, I'm happy to answer them on Slack. And thank you.
Thank you, Bart. Do we have any questions? Wolfgang has a question here for you.
Thank you very much, Bart, for a great talk. Very excited about the code. So one of the questions I had was, you said you don't do radio transfer, but I'm wondering, are you doing radio transfer for the gamma ray deposition? How do you do the gamma ray deposition?
Yeah, for the gamma ray deposition, I do radiative transfer. So we say, okay, in this zone, we have this much nickel that's going to decay over this time scale. They're going to send out this much gamma rays. Where are they going to get absorbed? So in that part, I do radiative transfer.
Then you use Spencer-Fano, and use that for your population and for your ionization. Okay.
Yes.
Thank you.
Thanks, Wolfgang, and thank you, Bart. Okay, so we're gonna cross the North Sea and move into England at this point. And I'd like to welcome Florian Kirchschlager from Ghent University. They will be talking about dust destruction in supernova remnants, and this is a 15-minute contributed talk. Welcome, Florian.
Yes, thank you very much. Can you hear me? Okay. Okay, yeah, indeed, I'm not in England anymore. I was at UCL a couple of years, but I moved to Ghent in Belgium a few weeks ago. And I'm working now together with Ilse. And yeah, my research topic is dust destruction in supernova remnants. And yeah, it's mainly about Casey. I'm going to talk now in the next 12 minutes. So dust destruction in supernova remnants, can we see dust destruction observations? The clear answer is yes, we can. For example, in Herschel observations, we have a spatial distribution of the dust mass, and we can clearly see that within the inner shock wave, so within the reverse shock, we have much more dust per pixel than in outer regions, and then we can calculate that around 70% of the dust is destroyed when the reverse shock destroys the dust. Same is true when we look at the SED from Felix Presley. The blue line gives the amount of dust which is unshocked, and the red line is shocked dust material. And when you take into account where the position of the shocks are, then you end up at around 80 to 90% of dust which is destroyed in these models. I want to focus on the numerical side of this. Can we calculate how much dust is destroyed? There have been a lot of studies in the last 15 years which are investigating the dust destruction in supernova remnants, and they all end up at completely different values of how much dust can survive. And we are in a range of 0 to nearly 100% of dust destruction. The main reason for these big range is that each study, or nearly each study, takes different assumptions into account and models completely different processes. The most important processes for the dust destruction in supernova remnants are the sputtering, and we can distinguish between thermal sputtering and kinetic sputtering. So on the one hand, we have very hot gas, on the other hand, we have fast gas. They are colliding with the surfaces of dust, and then dust atoms are removed from the surface of the grains. And the other thing are grain collisions, which are often neglected, but which can also have a big impact on the dust survival rates, as we will see. And in total, when you take into account all these processes, then the freshly produced dust can be destroyed already in the supernova remnant. So, and the two questions we want to focus on is how much dust can survive, and the second one is which dust can survive. So I already mentioned the shocks. I want to briefly show you what I mean by forward shock and reverse shock. So this is a model of the ejecta of a supernova remnant. So in the center we have the explosion of our star. We have in green or light green our ejecta or unshocked ejecta with clumps. And then the red arrows show the forward shock. And when the forward shock is impacting the circumstellar material or ISM, then a reverse shock is created, which is going backwards to the center of the ejecta. And in the clumps, we assume that the dust forms. So what we have then is we have a clump of gas and of dust, and the reverse shock is going just into the direction, and then the dust can be destroyed by the reverse shock. Instead of modeling a full ejecta, we focus on such a small box, which is shown here in red. So we have only one single clump, and we have a shock wave which is impacting on this clump. And then we assume, okay, when we have the dust destruction in this single clump, we can extrapolate it to the full remnant and say something about the total destruction rate. So this is then the clump crushing scenario, clump crushing problem, one single clump in an ambient medium. And the shock wave is impacting this clump. We make then MHD simulations with the code and simulate how a planar shock is impacting with such an overdense clump. Typical gas densities or over densities are 100. So we have 100 gas particles in the clump and only one particle in the ambient medium. And as you already saw in the movie, so when the shock wave hits the clump, it is disrupted, it is compressed, and then it's accelerated and also fragmented. The problem here is this is only the gas. So you don't have any information here for the dust because there are some attempts to implement everything into hydrocode or MHD code, but it's not possible so far to take into account as many processes as we want to, because grain collisions are very expensive in time calculation and so on. So what we did then is we made our own, or I wrote my own code. So it's an external dust processing code, a post-processing code, which uses the output from the MHD simulations, so the gas velocity, gas temperature, gas density, and also magnetic field. And yeah, then we can calculate the transport of our dust grains due to gas and plasma drag, and now also for magnetic field forces. The dust can be charged. We consider Coulomb forces and also magnetic fields. And the two main processes of dust destruction, as I already mentioned, are sputtering. So we move dust material from the surface of our dust grains and we get smaller dust grains. And the other thing are the grain collisions. And here we have to distinguish between, on one hand, we have fragmentation. So big grains are smashed into or fragmented into smaller fragments. And the other thing is if our collision velocity is so high that the threshold is then the dust grains can be completely destroyed and are immediately vaporized. So we have vaporization and total destruction of our dust grains. Okay, then what are the main results which we can see in this clump crushing scenario? So first thing is a decoupling of gas and large dust grains. At the top left, you see the same simulation as before. This is the gas. Top right are the small grains, around 6 nanometers. They are very well coupled to the gas, so that's why it looks very similar to the gas distribution. Bottom left, a factor of 10 larger dust grains. You see already differences because it starts to decouple from the gas, and the big blob here represents very big grains, 500 nanometers to 0.5 micrometer. It takes much more time to accelerate all these dust material. The dust survival then depends on different parameters. Most important are the grain size, which is here on the x-axis. And on the y-axis, you have the dust survival rate. 100% is very good, 0 is total destruction. And the different lines show different clump densities. So if you have very small clump densities of only 50, then it's a very rough trend that small grains are completely destroyed and big grains can survive. And there's a trend, when you increase your clump density, then the tiny grains start to decouple, or the tiny grains are coupled to the gas, are transported, are not ejected in the ambient medium, and that's why they are protected and can have a higher survival rate. In the intermediate range, you still have high destruction rates here, as this is due to grain collisions. When we directly compare sputtering and grain collisions, we can see that there are very different trends. So again, let's start with the easy thing, grain collisions. If the clump density is very low, then also the dust number density is quite low, and we have not a lot of collisions, so there's not very much destruction due to grain collisions. It changes when we increase our clump density, then also the destruction by grain collision gets more and more important. Sputtering is a little bit more complicated because we have here two trends again. So one thing is, the bigger the grain, the harder it is to destroy the dust grain. So this is very clear for the small clump densities. For the big clump densities, so 300 and 1000 again, we get another process acting for the tiny grains that the gas drag is much more effective there, which accelerates the dust grains much better. And then the dust grains, the tiny dust grains, are very well coupled to the gas and protected within high clump gas densities and are not suffer destruction by hot gas, by the hot ambient medium gas. Yeah, so this plot just shows that grain collisions plus sputtering are not the same as when you simulate both together. So grain collisions not always destroy a lot of dust material. That's because fragmentations or vaporization sometimes destroy only a small amount of dust, but creates fragments. Fragments are not destroyed dust material, but they are only smaller dust particles. And these can then much easier sputter it. So this means if you add both processes together, the total destruction is much more effective. So that's why you have this synergistic effect here, that the biggest dust destruction is if you combine both processes together. My second last slide is something that in the opposite direction, that we also could have dust growth. So there are 3 different dust growth processes. The first is sticking, which is not very important because the collision velocities are in general too high. The second thing is gas accretion. So if the gas is below a certain velocity threshold, it can accrete on the surface of the dust grain. And the third thing is something which hasn't been studied before, which is related to the sputtering. So when an impinging gas particle is colliding with the dust grain, it can eject an atom from the dust grain surface. But what is happening in this case with the impinging gas particle? If the penetration depth of this gas particle is high enough, it can penetrate into the dust grain and can stick there. And in Casei, we are very oxygen rich. So this means we have oxygen, silicates, and magnesium ions there, which means that we get a lot of more contribution to silicate dust material. And taking this into account, we can increase in some cases the surviving dust mass by a factor of 2 to 4. So which could be quite important if you want to increase our dust survival rate. And then the last thing is, yeah, what about magnetic fields? The charged dust grain in a magnetic field means that it is deflected from its original trajectory. You have a gyro motion of your charged dust grain around the magnetic field. So it's spinning around the magnetic field lines, or spiraling around your magnetic field lines. And then you can see different effects on different grain sizes. For the small dust grains, this means it decouples from the clumped gas, and the dust can much easier be destroyed. The other thing is that, and this is particularly important for big grains, so micrometer size grains, that you have higher collision velocities of your dust grains, and then also there you have a higher dust destruction. And when you have look at the plots, in dark blue is the dust survival rate for without magnetic field, and when you increase your magnetic field strength from 0 to 10 microgauss, so this is the initial magnetic field strength, then you see that in general the destruction rate increases, the survival rate is going down, and this is for all, or we can see this effect for all clump gas densities from small 50 to big 1000 clump gas density. Okay, and then that's it. Yeah, I've presented our dust processing code, paperboards, which is able to simulate dust destruction, dust transport, and dust growth. We use it to calculate the dust survival rates in Supernova Remnants, but also for the blast wave in the ISM. But in general, it's applicable to many different scientific cases. And in particular for Casei, we can see these 5 points which I've presented: a decoupling of gas and large dust grains when they are in a moving gas. Dust destruction is strongly depending on clump densities and grain sizes. We have destruction or dust growth effects like ion trapping, and granular collisions are sputtering out synergistic. And the last thing is, there are some words missing, magnetic fields cause a higher destruction. So, and that's why I'm finished, and I thank you for your attention.
We have time for one question. Online or, oh, sorry. Oh, can go ahead.
I already have my question. Thank you very much for a really nice talk. So one of the things that we did a couple of years ago, we were looking for companions in Cathay, and one of the discussions was how much stuff is there to hide companions and how deep are our limits. So I'm wondering, maybe you mentioned this already, do you have new limits for Cathay, AV limits for Cathay, for the center of Cathay?
What do you mean? Which limits do you mean? I didn't get it. Sorry.
That's like, extinction limits, that's extinction limits. I know you're working in a group where this work is present. I was wondering if you can comment on how much stuff there might be in Cathay. Upcoming study.
Yeah. So I'm not directly working on the extinctions and so on, but yeah, I think the most difficult problem in modeling the observations is with the grain size, indeed. So the modelers often assume that we have grain sizes in the range of 0.1 or 1 micrometer. And this is something that I find, and I think the extinction then strongly depends on which dust grain size you assume. It's also a problem for me that you see that my results strongly depend on the initial grain sizes. And if I take 0.1 or 1 micrometer, I get completely different results.
But can you sample over the prior range?
Again, please.
Can you sample over the prior range?
Yeah, I can. Yeah, so I assume different dust grain sizes, and then I get it's much better to protect the 1 micrometer dust grains compared to the 0.1 micrometer.
Thank you.
Zhang Yi had a question. I think we'll let her ask it. She has her hand raised.
Okay, hello, can you hear me?
Yes.
Okay. So you have hydrodynamic simulations and show the destruction rate depending on the density. Is it possible you can do, the clumps has different layers of density. Inner part might be more higher density, outer part is maybe lower density. We trace by optical and infrared in different regions. So, I mean, is it possible you can account for those factors and, estimate more realistic dust destruction rate?
You mean within one single clump or different clumps? So, but in general, both yes.
Yeah, single clumps, even. I mean,
in a single clump, sure. Yeah, we could assume a profile and then take into account these different gas density and also different dust number densities within a single clump, and then see what is the difference. I'm not quite sure if this makes such a big difference because it's mostly depending on, or the dominating factor is how much gas you have there, indeed.
But it wouldn't be the outer layer, plays a role of shielding the clumps, so it can prevent, dust destruction.
Yeah, but then you would also have probably not so much dust present in the outer parts, right?
Right.
So yes, but to answer your question, yes, it's possible. Yeah, there are a lot of free parameters to play around. And yeah, something I didn't show, so also changed clump radii, and the effect is, interestingly, you can see an effect, but it's not so big compared to the other 3 parameters, clump gas, density ratio, grain size, or magnetic field strength. So clump size matters, but not so much as the other 3.
Okay, thank you for the nice talk.
Okay, thank you, Zhang Yi, for that wonderful question, and Florian for a very nice talk. At this point, we're going to move on to a lightning talk exploring the late time near infrared plateau in Type 1a supernova by Maxine Deckard, Trinity College and University of Portsmouth. Maxine, welcome.
Great, thank you. I hope you can see my slides. That's all good. Yeah.
Yes.
Cool. So my name is Maxime Dekkers, and I'm going to talk to you very briefly today about the late time near-infrared plateau that we see in type 1a supernovae. So a very brief background. Back in 1980, Axelrod predicted the IR catastrophe, where essentially we expect a lot of the flux from the optical and near-infrared to be redistributed to the mid-infrared. And as a result, you'd expect in type 1a supernovae a very fast decline in the optical and near-infrared. However, this wasn't seen in any of the observations. But then models by Franzen and Jerkstrand in 2015 you introduced 2D mechanisms, which are UV fluorescence and multiple scattering. And it turns out that these two mechanisms are very good at redistributing flux from the UV into the optical and near-infrared. And this then accounts for not seeing the IR catastrophe and also the near-infrared plateau. So the near-infrared plateau we see between about 200 and 500 days in type 1a supernovae. It was first seen actually quite a long time ago. So I'm showing 3 light curves here for 2000 CX, 1998 BU, and 2011 FE. For 3 of these supernovae between about 250 and 500 days, you see a plateauing in the J and H bands. However, here you don't see this in the K band. Then in 2020, Orgrauer published the first sort of sample paper of these type 1As on the near-infrared plateau. So what I'm showing here is a H-band light curve, and in this paper he had data, near-infrared data for 9 type 1As on the plateau. And you can see the plateau here between 150 and 500 days. In the sample, all of the type 1As show this plateau, so there seems to be quite a universal property across type 1A supernovae. However, there wasn't a whole lot of data in the J and K bands in this paper, so we couldn't quite see whether this property extends to all of the near-infrared bands. So this is where our new work comes in. We've essentially been able to extend the sample by 12 supernovae, so this more than doubles the previous sample that we had. And the main nice thing is that now we've been able to populate the J and K bands. So on the right, you're seeing our new light curves with the new data across the 3 different bands. And what we see is that the J band certainly does have a plateau as well, but in the K band, we don't really see a plateau. And with this new data, we also are able to populate the H band with more data, which is nice because now we can study the plateau in a bit more detail. In the plot on the right as well, I'm showing a comparison to models here. So these are sub-Chandra mass models produced by Luke Shingles. As you can see, they reproduce the data really nicely in the J band. There are some discrepancies in H and K, which I don't really have time to go into, but I'm very happy to discuss on Slack if anyone has any questions about that. But I should also note that here the comparison to sub-Chandra mass models doesn't imply that we can't model this near-infrared plateau with Chandra mass models. We just haven't done that comparison yet for now. And then I just want to delve into the plateau across the 3 different bands in a bit more detail and compare that to the spectral evolution to see if we can make sense of this. And so in these plots on the left, you'll see the light curve data for the full sample, where here we fitted this with a 2-component linear model. We've been able to fit all of the data at the same time because the near-infrared shows very little intrinsic scatter. And so we've just clumped all the data together in absolute magnitude and performed this fit. And so for the J band, as I already mentioned before, we do see this plateau, and it's well modeled by the model. And on the right, you're seeing the spectral evolution of 2014J, which was published by Diamond in 2018 across 4 different epochs. And we expect to see this plateau in the J band because the J band is dominated by these iron 2 features, which seem to remain constant throughout the plateau phase. However, if we move to the H band, we still see a plateau, but we see a bit more scatter across the data. And if we look at the evolution of 2014J, this could be explained by the fact that there's these other features present. So it's still dominated by this strong iron 2 feature, which doesn't evolve during the plateau. But then if we look at this feature here, where I've just crossed out the non-dominating factors here, but this feature is dominated by cobalt 3, and cobalt is still expected to decay to iron during this plateau phase. And similarly, the feature on the right, which is also decaying during the plateau, is dominated by iron 3 and cobalt 3, where again the cobalt's decaying to iron, and the iron 3 is expected to recombine to iron 2. And so the models also predict a slightly steeper slope in the H band compared to the J band. And then finally, looking at the K band data, we don't see a plateau at all here. So this 2-component fit prefers just a 1-component fit in a continuous decline. The models predict the same thing, and if we look at the spectra, this also makes perfect sense because the K band is completely dominated by this iron 3 feature. And so here the iron 3 is recombined to form iron 2, and throughout the plateau, this feature is losing its strength. So brief conclusions, we see the plateau in the J and H bands, but not in the K band. Our data is really well produced by the sub-Chandra mass model, and really easily explained by the spectral evolution of 2014J. So I encourage any questions on Slack. There's a lot more work we've done on the plateau, but not a whole lot of time to present it. So do message me or keep an eye out for a paper that will be coming in the next few months. Thank you.
Thank you, Maxi. And I apologize if I pronounced your name. We don't have time for questions, but as she suggested, if you have anything, questions or comments, please hit her up on Slack. There's a lively discussion that's already ongoing on some of the topics that have already been discussed here today. So I'd like to move on to another lightning talk concerning 1A supernova. This is exploring early spectroscopic type 1A supernova. This is by Jonathan Pineda Garcia, Universidad Andres Bello, and Millennium Institute for Astrophysics or of Astrophysics. Welcome, Jonathan. This is a lightning talk.
Okay, hey. Can you hear me?
Yes.
Okay. So my name is Jonathan Pineda. Today I'm going to talk. My talk is focused in exploring early spectroscopic type 1A supernovae. So the motivation for our talk is that there are progenitors and explosion mechanisms that cannot be explained by a single model. We could have different interpretations for the same object using different models. So the reason is we need to explore early observations or spectroscopic observations in this specific case to constrain theoretical models. Instead of it, liquors or photometry is broadly studied by different models. For example, in the left panel, there is the Swift-Key transient facility data release. And Bullet et al. In 2020, they studied the colors of this sample at early phases. So as you can see, there is not an evidence of the diversity type 1A supernovae family as well discussed before by Steve Singer et al. In the right panel, from the liquor early features, we can see excess of flux that can provide us a hint about the progenitor star in the type 1A supernova. And also, we have there different scenarios to explore these early fluxes in the supernovae according to the properties of the explosion itself. So the reason that we are going to study from the spectroscopic point of view, early spectroscopic point of view, is because we can obtain from spectroscopy the kinematics and also the composition of the supernovae at early stages. So there are different models that classify type 1A supernovae according to these spectroscopic properties, as there is the silicon absorption lines, that it is the strongest at early phase. But all these classification systems are based or are focused on maximum light. So the idea here is for us, we have early spectroscopic observations for type 1A supernovae. So we are going to cover for the most early part of the spectroscopic observations up to the nebular phase part of these two objects that we have already in hand. Studying mainly the silicon 26355 Armstrong absorption line at early phases, and also the sulfur tau for the spectral classification. The difference in these two lines is that the silicon line is stronger at early phase, but the sulfur line is mixed. So at the end, we prefer to compare all the properties of the type 1A supernovae using the silicon 26355 Armstrong line. Here, as you can see, there is, here we reveal that exists two populations as Wang et al. In 2009 proposed, the normal velocity displayed as blue symbols and the high velocity displayed as red symbols. Thus, high velocity are these supernovae that the ejecta velocity of the ejecta is larger than 12,000 kilometers per second. So we have one in our observations, one high velocity that we provide to this small sample. also a normal type 1a supernovae. According to the color evolution, we also studied these properties. It's in agreement with the Bula et al. Study that there is not a preferred that displays different populations at the early phase, as was revealed by other studies. And finally, from the spectral evolution that this is that we are going to focus in our research, we are trying to compare with these type 1a early supernovae, even normal, high velocity, or subluminous, in order to see what are the properties of these supernovae at early phases. Because you know that at the very early phase, we are seeing the ejecta recently after explosion. So most of the models are based on the maximum light. And this part of the early spectroscopic observations are missed for that reason. So we propose to constrain theoretical models from our observations and increasing this sample of type 1a supernovae at early phases. Here, for example, in the bottom right panel, you can see one interesting property of the high velocity supernovae for the silicon line, that it is blue shifted if we compare with those of normal velocity, the dashed line. So we are trying to explore more about this high velocity type 1a supernovae in order to obtain more clues about this spectroscopic family. So thank you very much. I'm glad to answer your question via the Slack channel.
Thank you, Jonathan. And yes, I think we'll keep questions in the Slack channel. It's very interesting. Excuse me. So we have one more lightning talk this morning and then a contributed talk. So we'll go to our last lightning talk for this session, which is Chelsea Braun will be discussing progenitors and explosion properties, of supernova remnants hosting central compact objects. She's from the University of Manitoba. Welcome, Chelsea.
Hello, you can hear me?
Yes, you can.
Okay, and hopefully see my slides. Okay. All right, so hello, I am Chelsea Braun from the University of Manitoba, and for my PhD thesis work, I looked at progenitors and explosion properties of supernova remnants hosting central compact objects that show evidence of enhanced ejecta using primarily Chandra data. So one of the major goals of this work is to estimate the progenitor mass of an SNR. This is done by comparing the theoretical explosion models to the observational data. From the theorist's perspective, they develop complicated stellar explosion models that can output nucleosynthesis yields for some variable parameter, which is usually the progenitor mass and sometimes the explosion energy. From the observer's perspective, we look at the spectrum of young ejecta-dominated SNRs and fit the data with plasma shock models in order to estimate the abundance yields. By comparing the nucleosynthesis yields from the theoretical models to the abundance yields from X-ray spectroscopy, we can estimate the progenitor mass. So the SNRs in this study consist of G15, Cas79, Cas-A, Puppis-A, G349, and G350. For this presentation, we will look at G15 as an example. So this is a systematic study, and so we decided to select regions using an algorithm that creates regions of nearest neighbor pixels with similar surface brightness. This is done because there is evidence to suggest correlation between surface brightness and physical parameters like density, temperatures, and abundances. So this also maintains the morphology of the remnant in the regions themselves, and you can see this for our Cas-A, which is our highest quality data, where the region selection image still ends up looking like Cas-A. And for some of our lower quality images like G15, we still maintain that bright shell structure in the south. So once region selection is done, we extract the spectra and then fit it with plasma shock models appropriate for modeling young SNRs. We attempt to separate the forward shocked ISM from the reverse shocked ejecta, either by modeling the two components, the soft and the hard, together, or if one component dominates over the other for a region, only a singular component is necessary. So through this method, we can determine the elemental abundances for estimating the progenitor mass. So we do this by taking the averages of the abundances for all the regions of an SNR and ratioing them to silicon in order to compare the nucleosynthesis yields to 5 of the most used explosion models. So each model here gives the elemental yields for a particular progenitor mass, and then our observed data is overplotted with the black X and the error bars. And what we find is that none of the abundance yields match any of the models for all of the elements. For example, here, this is G15 data. It only matches for magnesium across all the models. And additionally, it is not necessarily the same progenitor mass that fits the data between the models themselves. And this is true for all of the SNRs in this study. And therefore, our final progenitor mass estimates are only dependent on a few elements that fit well rather than all of them. Additionally, we also performed the first systematic study that explores degeneracy in the explosion energy with the Fryer 2018 model. The Fryer model looks at 3 progenitor masses with a wide range of explosion energies. Additionally, we also look at asymmetrical explosions where we linearly combine different explosion energies to try and best fit the data. So to wrap things up, we list our progenitor mass estimates here in the table for each SNR, and I snuck in RCW 103, which was from a previous paper. And in conclusion, this was the first systematic study of SNRs against all of the most used explosion models in the literature, and the first to explore degeneracy in the explosion energy. And I look forward to the paper on this in a couple of months. Thanks.
Thank you, Chelsea. I hope that Samar still let you graduate after you found that none of the abundances stay in the models. Do we have any questions for Chelsea? Go ahead, Wolfgang.
Very nice talk. So I'm wondering, like, you know, if you could in your selection function, we have your content algorithm being lumping together regions that have like different sort of different physical properties, and that's why you get the wrong abundances.
It's definitely possible.
Do the different algorithm and then do it again and then see if you get different ones. You know what I mean?
There's an idea. Yeah. I mean, we can enter a lot of variables into the algorithm itself, and that would drastically change. Well, not drastically. It will change the looks of the regions themselves. So I guess that's a good way of looking at it to double check our work.
Thank you. I see that Rick has a question online.
Oh.
So Chelsea, this was great. I want to encourage you to go a little bit out on a limb and say that to me, the obvious conclusion from your results is that if you can't match a bunch of elements, more than a few elements from a model to these observations, that tells you that the models are crap.
Your words, not mine. I'd be kinder.
Well,
yeah.
Don't be. You know, the community moves forward by having this pointed out. Now, almost all the models you're putting here are 1D. They're not neutrino-driven explosions. All of these things are things that we know affect the nucleosynthesis. The sad reality is that models that do a better job with the nucleosynthesis can't be produced in the large numbers that these can. So as a community, we have to figure out a way to produce decent nucleosynthesis predictions from models that have more physics than these do, somehow.
Excellent point. And I'd just like to have one last quick question from Carlos, and then we'll move on.
Yeah, it's more a comment than a question, but if you select by surface brightness, you may be focusing on regions with particularly strong circumstellar interaction, and that may be completely unrelated to the underlying exposure in terms of spatial morphology. Just keep that in.
Okay.
Okay, let's thank Chelsea again, and let's move on to our last talk of the day. Excuse me. No. Okay, and I'll thank you. So our last talk today, also a slight modification. After this, we're going to still have a 30-minute break, and we'll reconvene at 11:15. Our last talk of the morning and try that for the third time. It's by Martin Laming from NRL. He will be talking about elemental abundances in the unshocked ejecta of Cassiopeia A. Welcome, Martin.
Hello, can everybody hear me?
Yes.
And you can see the slides. Great. Okay, this is a talk about the, based on a paper here, Martin Laming and Thea Tamim, we did earlier this pandemic, 2020, where we studied the element abundances in the unshocked ejecta of Cassiopeia A. This will complement a paper, an earlier paper I did with Una Huang, where we studied in Chandra X-ray data the element abundance in the shocked ejecta. So unshocked ejecta. Well, first of all, let me just quickly summarize the X-ray results. Here we measured the mass of each element, oxygen, neon, magnesium, silicon, sulfur, argon, and iron, determined from X-ray spectroscopy. And this is a direct, well, as direct as you can from spectroscopy measurement of the mass. And you see here that the remnant we see is mainly oxygen. Other elements are sort of at solar or subsolar concentrations relative to oxygen. The mass of X-ray emitting ejecta is around 2.84 solar masses. We also measured the velocities of these various elements with respect to the explosion center and discovered that the recoil of the remnant is approximately anti-parallel to the recoil of the compact central object, which is starting to suggest a hydrodynamic kick as the mechanism for the compact central object recoil. We're also showing here on this plot that the strong iron regions, which we will try and address, which have been addressed by several people, I'll try and mention a bit later on in this talk. So for the Spitzer data, here you see the image of Cas A in the oxygen 4 25 micron line. You see bright regions around the reverse shock, and you see a dim region in the center. We are going to be interested in the dim region in the center, that the bright regions are thermally unstable portions of the reverse shock that actually comprise rather small amounts of mass and are very difficult to model. So we're not really interested in those. We want the quiescent, expanding, ballistically expanding ejecta in the center. So we're going to concentrate on region 1, shown here in this high resolution map. Now the spectrum from region 1 is given here. This was fitted by Thea Tamim. My understanding is that Thea just threw in Gaussians until she got what was a reasonable fit, without actually knowing where we expected lines to show up. As it happened, you can interpret the fits that Thea found here. Each column here corresponds to the 6 components of the oxygen 4 25 micron feature. The strong lines here and here we identify with reverse shock. The lines on the outside we identify with either the expansion of ejecta coming towards the reverse shock, or ejecta that are in dense clumps and not strongly decelerated. And the regions we're interested in are these 2 regions here. So not only do we want the faint regions of the image, we want the even fainter regions of the spectrum that faint region of the image gives you to actually properly understand the unshocked ejecta. My understanding is, I said, Thea didn't know what numbers we were looking for, but here are the numbers for uniform unclumped ejecta. The reverse shock speed should be 2450 kilometers per second, according to a simple 1D Supernova Remnant model. The pre-reverse shock expansion speed should be around 4,000 kilometers per second, which gives you a post-shock expansion speed of sort of 1668 to 2280 kilometers per second. This is assuming a fully radiative shock to a gamma equal 5/3 shock. Of course, if the oxygen is clumped and is not, the reverse shock speed is lower, and stuff will sail through the reverse shock and be decelerated less. So we're fairly confident saying that this and this are not what we are interested in. This is stuff excited by the reverse shock, and it's the inner two Gaussians that we really want to concentrate on. We only have high resolution spectra over this region 1. We have low resolution spectra over the whole inner region. Here it is. And so all we do is assume the same ratio of quiescent ballistically expanding ejecta emission to the total line profile for the region 1 as we do for the whole inner region, and we make some geometric corrections. And so we can get an estimate of the mass from the flux. And here I'm giving you a quick sample. The mass of oxygen in the inner ejecta is about 0.14 solar masses from the various corrections we do. And now an important feature of this work is that I'm telling you here, going straight from line intensities to ejecta mass. This is not quite a good thing to do. Spectroscopy tells us the emission measure, NENIV. And so we need some measure of the electron density or the volume to be able to convert our line intensity into an element mass. If you had uniform ejecta, then in the shocked ejecta, the X-rays would have a strongly non-uniform radial profile like this. And in the X-ray analysis, Una Huang went away and fitted 4,319 ejecta regions to build up masses of elements and we have small ejecta regions. We can estimate the volume. It still amazes me that she was able to make this work. 4,319 ejecta regions all fitted. I'm a novice at computing, and she's obviously one of the real experts. Now, in the infrared, you've seen the quality of our data. We cannot split it up into more than one region, let alone 4,319. So we need to do something else to get an estimate of the density. And so what we do is calculate the ionization state of all of the elements that we're interested in as a function of density according to a photoionization recombination equilibrium. What is happening is that the inner ejecta are photoionized by radiation from the reverse shock and from the forward shock. And we just take this Chandra spectrum and add estimates of thermal Bremsstrahlung at each end, below 300 eV or above 10 keV, to get a photoionizing spectrum. And we calculate the ionization balance for all of the interesting elements under this model. So here you're seeing oxygen, silicon, sulfur, and iron going from, this is a density in atomic units per cc. The average density in CASA today should be about 0.6 AMU per cc, so about here. So you would expect oxygen to be somewhere between lithium and helium-like, yes, around helium-like charge state. Silicon will be, I haven't labeled these, but this is something like boron-like. And so if we're seeing, for example, oxygen 4, the boron-like charge state of oxygen, when it ought to be helium-like, it must be clumped. The density has to have to increase. So the recombination rates increase, but the photoionization rates remain the same. And that suppresses the degree of ionization. Here I'm showing you the run of electron temperature with density. Now the electron temperature is calculated from photoelectric heating, radiative cooling, cooling by adiabatic expansion. And so you're getting something at the low densities of around into the 10 to the 4, 10 to the 5 range. And at the high densities, it cools right the way down. Oxygen 4 is coming from this region where we're between sort of 100 and 1,000 degrees. Lower charge states are going way down. And here I cannot find a solution, a stable temperature solution. It goes right the way to 0. And here is the run of density. Importantly, iron in this case would be iron 8 if we had uniform density ejecta. So we take the density from these plots and calculate the masses of emitting elements. And here it is. Repeating the table I showed you at the beginning of the talk with the X-ray emitting masses in black. The new infrared data is given in red, surprise, surprise. And you can see here, we've got 0.14 solar masses of oxygen. We've got 0.31 solar masses of silicon. The inner ejecta are mainly silicon. The outer ejecta are mainly oxygen. The silicon is now much more strong in the inner ejecta. Also, some of the other intermediate Z elements are coming up a bit stronger relative to oxygen as well. So we see sulfur, we see neon. Interestingly, there is no iron that we can see. So we still have 0.14 solar masses of iron from the X-ray analysis. And this gives we have a total mass of infrared emitting ejecta of around 0.5, I gave 0.47 with generous error bars given the assumptions we make. And that gives a total ejecta mass of 3.31. So next question, where is the iron? We believe the ejecta are clumped because the iron, nickel, cobalt, iron radioactivity inflates bubbles, and that compresses the surrounding ejecta. So we expect the iron to be in tenuous, in underdense regions. So all I have done here is made a table of the various iron lines you might expect to see and estimate where they form at what density, calculate the iron fraction, calculate the surface flux and the maximum iron mass that could possibly be there if iron were filling the gaps that we're not seeing in oxygen and silicon. Iron 8, of course, this requires a little bit of compression to form this, and this would be a huge iron mass if it were true. And I'll show you on the next slide that it's not. That the other iron forbidden lines that we could go for, iron 10, iron 11, iron 13, iron 14, all give successively lower masses of iron if the remaining volume inside the reverse shock were filled with iron. So iron 8 line is there in the Spitzer data. It's at the extreme short wavelength end. If you notice carefully, the background subtraction has been over enthusiastic because we have negative counts per bin, but there is a positive excess in iron. I told you that we expect it to be about 0.55 solar masses if all the available volume were filled with iron 8. This line implies 0.01 solar masses of iron, if this iron 8 detection is real. So we strongly believe that actually the iron is much more highly ionized than iron 8. It's probably much more highly ionized than 10, 11, 13, or 14 as well. So we're probably looking at a rather low mass of iron inside the reverse shock to add to the 0.14 outside the reverse shock. So conclusions. The unshocked ejecta mass is about 0.47 solar masses with reasonably generous error bars given the assumptions I had to make to get to this number. Total ejecta mass is 3.3 solar masses. My prejudice, for want of a better word, is that the dust mass is probably rather small than other estimates I've seen in the literature. So I don't want to stick my neck out too far, but I would have guessed much less than the unshocked ejecta mass, so probably 0.1 or lower. There is no iron firmly detected in the inner ejecta. Probably most of the volume inside the reverse shock is filled with low density iron, but I think we are seeing most of the iron now, the Casset ejected in the X-rays. Iron infrared line should be a priority for JWST. What I would like to say is that given the Spitzer and Chandra data, the analysis I'm presenting here is probably the best job we can do in determining the complete census of elements produced by mass by Cassiopeia A. I should qualify that, of course, as until we get our hands on James Webb Space Telescope data, then there will be a lot more work to do. And so this is why I'm highlighting these lines. And the key innovation in this work is that calculating photoionization recombination equilibrium. Okay, thank you very much.
Thank you, Martin. Do we have any questions for Martin? Hold on, yeah, let me just check. Jung-Yi has a question.
Okay.
1 second.
Chris Fryer and
yeah. So Jung-Yi, why don't you go first?
Okay, can you hear me? Okay.
I can hear you, yes.
You use the low resolution spectra. There is a high resolution spectra.
We use the high resolution spectra for region 1.
Okay, but I
then
think
we assume the results from the high resolution spectra also apply to the low resolution spectra, which is coming from this whole region here.
I have seen high resolution usually showed better than that. They separated very well.
This is the high resolution oxygen 4 profile. We have many profiles, many different lines showing like this. And they all
But
show roughly the same double peak structure, which you can interpret as a reverse shock at the front of the remnant, the back of the remnant. And what we're after is the stuff in the middle.
yeah, maybe you can compare the velocity structure with the silicon line. So
Yes,
there might be,
they all show
there
roughly
might be,
the same.
there might be iron included here because I see more than typical number of,
Well,
different.
if there was iron here, it would be iron 2. And that
Right.
means it has to be strongly compressed. Iron 2 would be this one here. So it has to be in a very dense region. And it's,
Right. So what I'm saying is compare the velocity structure with the oxygen 4 and silicon 2, see if there is excess component. That
yes,
might
that has been
indicate iron.
done. I forget who did it.
I know Raymond did it, but I think it's a little different profile than you do. So I
Yes,
thought
yes.
you use the low resolution. Okay.
Yeah,
Anyway.
we have to use the low resolution data because that's the only data that covers the whole of the remnant. We only have
Right.
data here.
Right, but you can at least reserve, identify which lines there are. Oh, I mean, speech James Webb will do better, but it will cover very tiny areas. So
A very tiny area, yes.
right. So nice to have full understanding using spectral data.
Okay, I'm gonna move on to the next question by Chris Breyer. Just I think that's a very good but technical discussion on the quality of Spitzer data that could probably be followed on Slack. So Chris, you had a question as well?
Yeah, Martin, can you hear me?
Yes, I can hear you.
So one of the things that gets me excited about as we start to figure out where the iron is and what the distribution is how well can we take advantage of the titanium 44 results as well, because nickel 56 and titanium 44 tend to be made in the same place, although there's variations. If we can measure those variations and those differences, I think it starts to tell us a lot about the explosion properties. How likely is it that you're going to be able to connect these two and give relative locations of titanium 44? And unfortunately, it's nickel 56. Iron is different than nickel 56. It's spread out more, so we'll have to do some thinking. But it would be neat to see if we can get the iron and titanium co-location well mapped out.
Yeah, now I can't really tell you. I think we see most of the iron that Casey ejected in the X-rays. It's out, no, that's where most of it is. I think we have no confirmed detections of iron inside the reverse shock. So I don't quite know how, until we have some handle on what the iron is inside the reverse shock, I don't think I can really answer your question. My understanding is, from talking to you and others, is that there's quite a wide variation in iron, nickel 56, titanium 44 that can be produced by nucleosynthesis. And I think we're probably seeing quite a wide variation. But it's, yeah. As Young-Yi said, with JWST, we only are going to have a small field of view inside here. And so one of the thoughts we want to do is select a region and just go deep and see if we can see any iron at all. I don't know if that answers your question, but.
Chris, you're muted if you're talking.
I think as we get this data, this JWST data, I think it's going to really start to get exciting to
I
see
think so too,
how they
yes.
vary. Yeah.
Yeah, we did the best we could with Spitzer. Didn't really find any convincing iron. So the best one was this one. I think it's a real feature, but it's much weaker than you would expect. Naively expect. Okay.
All right. I see that Florian has a question, and then I'm going to go to Jaco after Florian, and then we'll take a break. So Florian.
Yeah, very quick naive question. So if the ejecta mass is 3 solar masses and the progenitor was around 20 solar masses, where is the missing mass?
The missing mass has been expelled as a wind for the explosion.
Oh, 70 solar masses, so much. Okay.
No, 17, yes, something like that. And we think this is aided by a binary companion.
Okay, good, thanks.
Yeah.
And don't forget the neutron star.
Yeah, it's about 5 solar masses when it explodes. Yeah.
Okay.
All right, Jakob?
Yeah, Martin, very nice talk, very nice result. I have just one question. How good is your equilibrium estimate? Because you have an expanding medium. Could it be something like electron freeze out?
The electrons, I haven't thought about that too hard. I assumed everything is sufficiently equilibrated to stay in photoionization recombination equilibrium. I think that's going to happen. What you're going to, in these denser regions here, you're probably safe in that approximation. But as you go to the more tenuous regions, I think things are going to freeze out.
And another question about the absorption that we see in the radio. In order to reduce the unshocked mass, what we really need is to have a low temperature, and your temperature estimate seems to be more like thousands rather than 100 Kelvin.
Okay, the temperature estimate at oxygen 4 was around 1,000, but it's cooling dramatically here because of the oxygen 4 25 micron line. And once you get down to where you have silicon 2, iron, silicon 2, sulfur 2, sulfur 3, here you're down to around 100 degrees. Going down, and I had to cut it off here at about 30 degrees. I can't find any stable solution here. So the sort of temperatures I'm getting here agreed with, for example, paper John Raymond did with on silicon 1, silicon 2. So I'm not too, I think this is fairly close, as correct as anything. Obviously, things could be done better.
You need new data, clearly. Yeah.
Sorry,
I can't hear you very well.
You need new data.
Yes, we do.
All right. So that concludes the morning session. We are going to take a break now until 11:15. I would like to note that that's different than what's in the schedule. We had a talk that was dropped at the last minute. So at 11:15, we will reconvene with an invited talk by Chris Breyer. And everything else should be scheduled. So if you're giving a talk in that session, just note the time. And thank you, everybody. Thank you to our online speakers and our one in-person speaker for this morning. And we'll see everybody back here in about 25 minutes.
One quick reminder is that the door over there is the door into the building is locked unless you have a key, ID. This one's also locked, but we'll prop this one open. So try to use this one or the main entrance in the front of our building. No, we can think about
It's like the one next to the yeah.
Great. I would say my notes, but you're the only one. That's fine. I mean, no, there's no anyone can be. Yeah. Then I like that idea. I have the. So when I'm looking like. Oh, right, yeah. And then someone okay. Okay, thank you. Yeah.
Yeah.